All right, this is my presentation on Euler's method. This is Leonard Euler, the person who developed Euler's method. So in order to understand Euler's method, first it's important to understand differential equations. A differential equation is any equation involving y prime, and x, where y is a function of x and y prime is the derivative of y. For example, y prime equals 3y over x. As you can see, it involves all the necessary components, y prime, y, and x, and y prime is a function of x, or y is a function of x. So you can see that in our solution. So our solution is y equals x to the third. So as you can see, y is a function of x. You can verify this solution by first finding y prime, plugging in y prime and y to get 3x squared equals 3x to the third over x equals 3x squared. So as you can see, this is a solution of this differential equation. Now, y equals x to the third is not the only solution to y prime equals 3y over x. It is one of many solutions. So differential equations have what are called general solutions. So the general solution to this equation is y equals cx to the third, where c is an arbitrary coefficient, where any value of c is going to be a solution of y prime equals 3y over x. So as you can see, you can plug these things in again. So find the derivative, that's 3cx squared, and plug everything in to get 3cx squared equals 3cx squared. Now, because the solution is y as a function of x, you can graph these solutions in what are called solution curves to a differential equation. This would be a graph of the general solution. So this is the graph of y equals cx to the third for every value of c. I obviously did not graph every single value of c because this entire graph will be completely covered because there are an infinite number of values of c, but I did graph a fair amount to illustrate that there are many different solution curves. So particular solutions. So particular solution would be one of those solution curves. So in order to find a particular solution, you need initial conditions to specify which particular solution curve you want. So for example, your initial conditions could be when x equals 3, y equals 9. So you can just plug this into your general solution, simplify to find your c value is 1/3, and your particular solution would be y equals 1/3 x to the third. You can graph this particular solution right here, and you'll find that you can see that this is the solution of y prime equals 3y over x that goes through the point 3, 9. Euler's method. Euler's method is a method of finding particular solutions to differential equations, because oftentimes finding the solutions, both general and particular, of differential equations is incredibly difficult, oftentimes impossible. Therefore, Euler's method is a method of approximating the particular solution curves. So because differential equations have an infinite number of solution curves, every point on the xy plane lies on a particular solution curve of a differential equation. So as long as you are given a point xy on the xy plane, those can be your initial conditions, and with that you can find the particular solution curve of the differential equation that goes through the point xy. Now, what is Euler's method? So first, you should understand the standard notation of a differential equation, and that is y prime equals f of xy, where y prime is a function of xy. So essentially, y prime is the slope at xy. So a differential equation basically gives a slope for each and every x and y value. So y prime would be the slope at xy of the particular solution that goes through xy. This is a little bit confusing, but you can think about it like this. At every single point xy, a particular solution of the differential equation goes through it. Y prime is the slope of the tangent line at the point xy on the graph of the particular solution that goes through xy. Like I said, it is a little bit confusing to wrap your head around, but Euler's method is a way of graphing an approximation of a particular solution curve by starting at a certain point, finding the tangent line at that point to the solution curve that it exists on, finding another point along the line, and repeating the process. So you start at a certain point, that would be your initial conditions. You find the tangent line of that point, and the tangent line is given, the slope of the tangent line is given by y prime when you plug that point into the differential equation. Then you find a new point along that tangent line and repeat the process by finding the slope of the tangent line of your new point and finding a new point on that tangent line. Like I said, it's slightly confusing to wrap your head around, but it shouldn't be too hard. So how to find new points in Euler's method. So you're given your starting point, your initial conditions, x0, y0. So we are finding the particular solution of a differential equation that goes through the point x0, y0. So to find our new points, we're trying to find x1, y1 by finding the tangent line at x0, y0, moving along it by a small change in x, and finding a new point x1, y1. So to find x1, that is the easy part. So x1 equals x0 plus h, where h is a small step along the x-axis. So h is your small change in x that you're taking along the tangent line to find your new point. So x1 is just x0 plus your change in x. So your starting x plus your change in x. y1 is slightly harder to find because you have to take your starting y and you have to add your change in x, h, times f of x0, y0. So to explain this, f of x0, y0 is the slope of the tangent line at the point x0, y0. H is your change in x that you're moving along that tangent line to find your new point. So change in x times slope, which is change in y over change in x, equals change in y. So what you're really finding by doing h f of x0, y0 is your change in y. And then you're adding your change in y to your initial y value to find your new y value, which is y1. This doesn't just work for x1 and y1 and x0, y0. You can put any value in there. So it really, it can be expressed by this formula with n's instead of numbers. So basically all this is saying is that your new x value is your starting x value plus h. Same goes for the y formula. So our Euler's method example. So we are going to find the solution for the differential equation y prime equals x squared plus y that passes through the point 1, 1, where h equals 0.1. So this is our differential equation, and our initial conditions are 1, 1. So we are finding the particular solution of this differential equation that goes through the point 1, 1. And we're finding it by moving along a series of tangent lines to find new points, and we're moving along those tangent lines by the change in x 0.1. So we have our starting x and y value, our starting point. Now we have to find our second point. So to find our second point, we can use the same process as illustrated on the previous slide, where we take x1 equals x0 plus h. We plug in our x0 and our h, and we simplify. Our new x value is 1.1. y value. To find our new y value, we're taking our starting y value and adding to that our change in x times our slope of the tangent line at x0, y0. So we're taking our starting y value and we're adding our change in y. And we're simplifying, plugging in, and then simplifying to get our new y value. I'm just once again reiterating that the point 1.1, 1.2 is on the tangent line at the point 1, 1. So we just moved along that tangent line by the change in x 0.1 to find our new point. So we obviously have to find more than 1 point to graph our particular solution curve. So it's helpful to organize all the points that you're going to find in a table. So we can start by doing x0, y0 is just 1, 1. Those were our initial conditions. x1, y1, which we just found, are 1.1, 1.2. Find x2, y2, we're using the exact same process. So we're essentially traveling along the tangent line at x1, y1, 1.1, 1.2. We're traveling along that tangent line by the same change in x, 0.1, to find our new point, which is 1.2, 1.441. So while to find x1, y1, we travel along the tangent line of x0, y0. To find x2, y2, we are traveling along the tangent line of x1, y1. So we just repeat this process again and again to find x3, y3, x4, y4, 5, 6, 7. So we just keep finding these points to, get enough points to draw a curve through and get a approximation of a particular solution. So I chose to find 13 points. So we're just repeating this process over and over and over again. And even when you get high numbers like x13, y13, you're just finding, you're just repeating the exact same process where we're traveling along the tangent line at this point by the change in x, which is 0.1. So we're adding 0.1 to x12 to find x13. And to find y13, we're taking y12 and adding our change in y. So we end up with all of these values, and now all these points. Now we have to plot the points. So there you go. And then connect the points with a curve. So this curve is our particular solution to the differential equation y prime equals x squared plus y that goes through the point 1, 1. So because y prime equals x squared plus y is a differential equation, the graph of the general solution would be an infinite amount of curves. But because we had the initial condition 1, 1, we were able to find a specific curve. Like I said, this is not the actual curve. This is just an approximation because instead of traveling along the curve to find our new points, we traveled along a series of tangent lines to the curve that we were trying to find. So thank you for watching.